Inte ens jag hade kunnat säga att jag står bakom det.
Okay, so let's get started. We will continue to talk about medium access control today, and then hopefully we'll have time to talk about one special example of a link layer protocol called Ethernet, a little bit about how this is actually implemented. We'll see how these generic methods that we've been talking to, how they could be implemented in a practical system. I guess you're all aware of the deadline, upcoming deadline for the project. So I hope it's going well. Again, I would like to remind you that the deadline is hard. So whatever you have at that time, you better submit it, because if you don't submit it, you get 0, right? Okay. So that's how it is. Okay, and then there was a question also when how to sign up for the actual presentation and oral exams and so forth. I don't think that has been organized yet, but it will be available at Ping Pong, and Shoaib will take care of that and email you all the details about that. Okay, so let's continue to talk about medium access control. So what is that? Well, this is a rather busy slide, so let's spend some time in going through this, even though it's review. So the idea is that we have a number of stations here. You can think of these as a number of transmitters, number of computers, number of users which are trying to use a shared medium. And we have the medium below here. So think of this maybe as a coaxial cable or radio channel or something like that. Then all of these stations 1, 2, up to capital N, have some data they would like to transmit over this medium. And for instance, there is a frame coming down here in station 1, and suppose that that's going to station N here. Then the time it takes from the frame to be available for transmission here until it's actually transmitted, until it's actually received, and perhaps there is also some retransmissions here, I don't know, but at some point this frame will hopefully pop up to the higher layers in station N here. The time it takes for this to be completed is called the frame transfer time. And this is typically something which is random. So we would like to control, say, its average value, or it's that 99% of the frames have a delay which is less than some number or something like that. So the delay transfer, the frame transfer time here is something that one would like to control. So that's one aspect of the whole thing. The other aspect is that we would like to support as much traffic as possible which is generated from these nodes here. So in general, one can think of that station number 1 is generating a number of frames per second, or frame per frame duration or something like that. But there is lambda 1 is the intensity with which station number 1 generates traffic that is supposed to go over this shared medium. At the same time, station 2 is generating lambda 2 and so forth. And if one sum all these lambdas together, so this is the, so this is the individual stations rates, frames per second or frame per some other time unit, and then the total load on or total offered traffic onto this shared medium is lambda. Okay, and this medium here has maybe some physical length d and some data rate which is supported by the physical layer that's operating on this medium, say r bits per second. So the frame duration and the frame length in bit are related through r as follows. So r, the rate on the medium, is nf, the number of bits per frame, divided by the frame duration. So that's the equation that keeps these three things together. Now, how much traffic is asked from the medium? Well, that's sometimes also called the offered data rate. And the offered data rate from all users is lambda times nf. And why is that? Well, if the lambda is like the frame per second, say, and then nf is bit per frame, then simple dimension analysis is that lambda times nf is in bit per second, right? And that is the traffic, total traffic that all these stations would like the medium to handle. If this traffic, okay, so another way to say that, is that a lot of traffic or not a lot of traffic? Well, then one can calculate the offered load, which is the ratio between the data that the nodes would like to transmit, lambda NF. These are the number of bits per second that the nodes would like to transmit. And we divide that by R, which is the capacity of this medium. So this is the offered load. And if this is going to be stable, this has to be less or equal to 1, right? If it's violating this, it's more than 1, then it's an impossible situation, because then the medium cannot support the traffic which is asked from it, right? But anyways, so the load, I guess, could be anything, but if we want it to be able to be handled by the medium, it has to be less or equal to 1. So the throughput is actually the data that gets through, okay? And it's sometimes also called the service data rate from all users. And suppose that's RU bit per second. Then there is a maximum load which is supported by the medium access control, sometimes called also maximum MAC efficiency. And it's the ratio between the best data rate we can push over the medium divided by the data rate's capacity. Okay, and this for sure is a number which is less than 1 due to MAC protocol overhead. Okay, we have to wait for access, we have to coordinate and so forth. Okay, and what is determining this rho max here is properties of the medium, and in particular one property which is crucial here, and that is the propagation delay over the medium. Okay, and the propagation delay is basically the distance of the medium, or the length of the medium divided with the propagation speed. So it's the propagation delay from the furthest away stations, okay, from station 1 to station N here. And the longer this time is, the harder it is to coordinate all these transmissions. It turns out, right? We showed that last time we saw. So the longer the distance is here, or rather the longer the propagation delay is between the furthest away nodes here, the harder it is to coordinate their transmissions. And this is captured in this parameter called the normalized delay bandwidth product, A, which is R, the data rate of the medium, times the propagation delay divided by the number of bits per frame, or a simpler equation is perhaps the propagation time divided by TF. So A here tells us how many frames that can fit on the medium at the same time. So if we think of it, that station number 1 is transmitting frames to station number N, how many frames can physically fit on the medium at any given point in time? Well, it can fit a packet of a certain number of bits will take up some physical number of meters on that medium. Okay, and then we can stick in the next frame here and the next frame here, say, and it turns out that the number of frames that we can fit into this physical length of the medium is exactly A. Okay, so we can think of A as the number of frames that can fit on the medium at the same time. Okay. Questions so far? No. Okay, if this is a little bit quick, that's fine, because it's a review. You can always go back and look at the last lecture to figure out what this means or get a slower explanation of this. Okay, so then we looked at, so this was setting up the MAC problem as such, and then we looked at the MAC protocol called ALOA, which is the simplest thing we can think of, is that whenever a station has a frame that's ready for transmission, it transmits it regardless, right? And then wait for an acknowledgement, and if the acknowledgement of that frame is not received before a timeout, then we back off a random time and then we retransmit. So it's possibly the simplest thing we can imagine when sharing a medium. For that particular protocol, we calculated very roughly what's called the normalized throughput. So it's the average number of successful frames we can transmit per frame duration. So again here, S, if that is it, it will be a number which is less or equal to 1, because it cannot be higher than this. It's 1, and we have a perfect medium access control scheme. Okay, and then we calculated this number S as the average number of successful frames divided by the frame duration. Okay, and the frame duration, as we know, is like TF before. And the average number of successful frames, well, that depends, right? How many frames do we get through the system? Well, it depends on how many collisions we have. And then we can calculate what is the probability of success, which is the probability of no collision. And then we can calculate the average number of frames. So the average number of frames is the average number of transmitted frames. Okay, so these are the attempts we do every TF seconds. These are the number of frames that we try to send over there. And then we multiply that with the probability that it actually goes through. Then we get the average number of successful frames. This quantity, this quantity, the ratio here is a number called G. So G is the average number of frame transmissions per frame duration. Okay, so and this includes then retransmission. So there are both new frames and old frames which are scheduled for retransmission. And then a very simplified analysis shows that S here has a very simple equation, G times E to the power of negative 2G when it's an unslotted ALOA, or G times E to the power of negative G when it's slotted. And if it follows like this, we can then calculate what is the best G, in the sense that we maximize the system throughput, S. And then it's easy enough to show that both of these will be less than S max, which is 1 over 2E for the unslotted case, or 1 over E for the slotted case. So basically we have something that looks like this, that if we plot S as a function of G, it is some type of curve like this, and then it's maximized for some particular G, let's call it G star, and then we get S max at that time for that G, right? So we know that the S here is 1 over 2E or 1 over E, depending if it's slotted or unslotted. So the question is then, can we do better? Because this is not very impressive numbers. So G is roughly 3 if you want. So for a slotted case, we basically get through 1/3 of the frames that we could possibly do. I mean, we know that S could be up to 1, but here we get 1 over 3 essentially. Is that correct? Anyways, whatever it is, yeah, I think it's correct. Whatever it is, the question is, can we do better, right? And you might have imagined that, of course, we could do better, because in ALOA here, whenever a station gets a frame to be ready for transmission, basically transmits that. It would be a smarter thing to listen to the channel first to see whether there is some traffic ongoing on the channel already, and if so, why even transmit? Because you're going to mess up the you're not going to get your frame through because it will collide with somebody else, and B, you will collide with somebody else's frame, and that frame will not get through. So it's basically a complete waste of time and energy and whatever to transmit this frame. So a better thing to do is to do what's called carrier sensing. And that basically is like ALOA, but you listen to the channel before actually doing transmission. Okay. And then the things we need to figure out now to specify the different types of carrier sense protocols is the following. If we sense the channel, if it's idle, then we transmit typically. But what do we do when we are busy? Well, then we back off. And here there are different strategies for doing this. So that's what we're going to talk about now. So any questions before we continue? Okay. So here, we are now in a medium access control problem. So we are all stations here, say, and then we would like to communicate. So before we communicate, before I say something, I listen to the room for a short time. Okay, it was empty, so then I can start to speak, right? It's basically what we do in a social environment. We listen if there's somebody else talking at the same time, and then we wait for a moment to, send our information. So it's listen before talk, right? But the question is, when you do this in a machine setting, right? You need some rules for about when do you start to talk after you determine that the channel is busy. If it's idle, it's rather simple, right? You just transmit. But if it's busy, what do you do? So then there are three main methods, where the third method is basically, the first method is basically a special case of the third one. So let's go through them. And that has, these are called persistence methods. And persistent means basically how eager you are to get your frame onto the medium. Right. So behavior then, variations of CSMA is behavior when sensing the channel and the channel is sensed as busy. So what to do then? The first rule one can think about is something called persistent or one persistent CSMA. And it's basically a two-stage process. We listen to the channel until it's idle, and the moment it becomes idle, then we transmit. Okay, so it's a very aggressive method, right? Listen to the channel, and the moment, the millisecond or microsecond it becomes available, then we transmit. So what could potentially be the problem with such a MAC protocol? Yeah, so exactly. So the suggestion here is the problem is that if many stations are waiting for the channel to become idle, they start to transmit at the same time, and then there will be a collision. Correct, right? So it's not a very good thing to do when there are many, when it can be believed that there are many stations waiting to transmit at any point in time. So when we have, say, high load on the channel. So the good thing is that there are very low delays, right? Because we basically don't wait anything, but then we can have many collisions, and then we have to handle the collisions, which in turn can generate delays, right? But anyways, for low loads, it has low delay and few collisions. As we increase the load, we will have more collisions, and therefore we have longer delays due to basically retransmissions that needs to take place. Okay, so if this is the aggressive method, then let's look at the very polite method, which is called non-persistent CSMA. And basically what that does is that when the channel is perceived to be busy, one back off for a random time, and this random time is fairly long, right? So it's like going to the post office and you see there is a line, then you go and take a cup of coffee for half an hour, and then you go back to the post office. Post office being the medium, right? And the coffee time being the back off. And then you go back and you see, is it available now? No, it's not. Okay, let's go have another cup of coffee. And you continue to do this until your channel is perceived to be idle, and then you transmit. So it's a more polite, less aggressive method. So we back off a random time, we sense the channel, if idle, transmit, if busy, we repeat this back off sensing cycle. And here we spread out the if many stations at the same time sense the channel and they sense it to be busy, then the next sensing time for these stations are randomized in time, and if that time is big enough, the selection of these back-off times is big enough, then there is a fair chance that these stations will not collide afterwards. Okay, so it has to do with how we design the random back-off time. So this has typically longer delays because we wait on the average a longer time before we try to transmit, but there are then fewer collisions. So, and then there is a sort of like a compromise between the aggressive and very non-aggressive method, and that's called P-persistent CSMA. And what we do here is we sense the channel and we back off it if it's busy. If it's idle, then with a certain probability, P, we transmit. With the other, and if we don't transmit, that is with probability 1 minus P, we do the following. we repeat sensing after a short delay, where the shorter delay here is called, let's call it t-slot, which is approximately equal to the propagation time. Okay, back-off time is typically much longer than the propagation time. So t-slot here is typically much less than back-off time. Okay. Okay. And then this parameter p determines the delay collision trade-off. And if we set p equals 1 here, then with probability 1 we transmit. Okay, which is the same thing as we do in a persistent CSMA. Okay, so let's look at pictures here. Maybe this is easier then. So here, one persistent is the aggressive one. So if we at some point in time would like to transmit a frame and then listen to the channel, it's busy. And then we keep on measuring the channel, we keep on sensing the channel until this point in time when it becomes idle, and then we transmit immediately, right? So this is the aggressive method. It's called persistent or one persistent CSMA. The other method here, which is non-persistent, is that when we measure the channel at this point in time, we see, oh, it's busy. And then we wait a back-off time, which could be substantial, right? In this case, it happens to be a fairly short back-off time, so then we repeat the sensing at this point in time. It's still busy, and then we wait another back-off time. And you see here that the back-off time is random. Okay, so it's different from time to time. So it's not a fixed amount of time, it's randomized. Every time we go into back-off, we wait a random amount of time. And in this case, we did a back-off to this time, and then the channel is idle, and then we transmit. Okay, and then P persistent is the following. We have a frame that would like to be transmitted at this time, and then we keep on continuously sensing the channel, and then here it's idle. Now we flip a coin and then decide whether to transmit or not. Okay, and if in this case it happens to be no, we should not transmit at this point in time. I mean, it's a random thing, so we could, but in this case we did not. So we wait a t-slot second. Okay, and then we repeat the sensing, and in this particular point in time happens to be so that the channel is busy, and then we back off a random time, and then after the back off we sense the channel at this point in time. So now we flip a coin again, and with probability p we transmit at this time. We did not, and therefore we wait another t-slot, and we flip a coin again, perhaps wait another t-slot, flip a coin again. Eventually the coin will be flipped such that we transmit. In this case it happens to be at this point in time. Right. Question?
Why does it continuously sense at the first t-slot?
So the question, why don't we continuously sense here? Well, one could, but this is not the way that typically this protocol is implemented. As a matter of fact, one should probably do it like this, that after the one should not continuously sense here. So in some books, this is explained so that we sense this. If it's busy, we wait a t-slot. Or if it's busy, we do a back off, and then we do sensing. And if it's idle, then we flip a coin. If it's not idle, we do back off. So there's several variations of this if you look in the book. So I don't have a very good explanation, except that this is the way it's been chosen in the book. Okay, any questions so far? So if this was if you rather have this explained in flowcharts, these are the flowcharts that corresponds to the verbal written explanation and also the pictures that were on the two previous slides. So So whatever you like, you can study all of these until you get a better feeling for what's going on. Okay, now improvements to carrier sensing is the following, that regardless of the persistence method we're following here, there is always a probability that we choose to transmit and somebody else choose to transmit at roughly the same time, right? So this does not get rid of all the collisions. It's just trying to limit them and limit the impact of these collisions. So for sure there will be collisions. Now if we start to transmit a frame and there is a collision, how do we detect that there is a collision? How do we know this? What is the basic method to figure out whether your transmission has been colliding with some other transmission? Yes?
It hasn't been acknowledged.
Exactly. So we listen for the acknowledgement, and if the acknowledgement doesn't arrive within the timeout, we know that something's gone wrong, right? So that's our way to standard way of figuring out whether our frame was colliding with something else or not. Okay. Is there a smarter way, faster way to figure out whether we have collided or not? What could we else do? So think about what do you do when you have a normal conversation with somebody? You listen as you talk, right? That's the thing, right? So when you detect that you are talking at the same time as some other person, you can quit talking, right? So that's called carrier sensing with collision detection. So if the hardware we have supports that you can listen to the channel at the same time as you transmit, we can detect collision in progress, and then we can abort the transmission because we know it's useless to continue to transmit because this message would anyways be garbled, and we don't have to wait for the timeout to figure this one out. We can do this faster. So it's a faster recovery, and also the length of the collision, we can limit that to a shorter period than the frame duration. Okay, so that's collision detection. So let's see how that works. So if the medium can be sensed while transmitting, and this is actually a big if, right? So this does not necessarily work on wireless channels. Because here, the reason for this is quite simple, because the transmitted power could be a billion times higher than the received power, okay? Which means that when you're transmitting, if you open up your receiver circuit, you might burn it, physically burn it, right? So that is typically not possible in wireless, even though there are experimental systems that can do this. This is not a deployed methods, I would say. So this is basically for wired type of medium. But if you can do this, then collisions in progress can be detected. And this is very good because then we can stop, right? So a collision typically implies that the frame is lost, and therefore it makes sense to stop transmitting the frame as soon as possible. As soon as we know it's colliding with something, we stop. So this is called CSMA, carrier sense multiple access with collision detection. And it works like this. We sense the channel. If busy, we act as persistent, non-persistent, or P-persistent, as we did before. If idle, we transmit. And here's the new thing. Okay, so this is the new thing. So this is collision detection. If a collision is detected during transmission, we stop transmission after a short delay. So we don't necessarily stop immediately, or if we stop immediately, we still keep on transmitting a little bit of data. And the reason for this will be clear later on. And then we back off at random time, and then we sense the channel again. Perhaps we use this persistent, non-persistent, or P-persistent CSMA, right? So the only modification now is that when we detect a collision, we stop transmitting. Okay. these two items here will be clearer if we go and look what's going on here. So here, a simple example. We have 3 stations, A, B, and C. At some point in time, at this point in time, A has a frame to be transmitted. So it senses the channel is idle, and then it transmits. It then reaches B at this point in time and C in this point in time. Right? Okay. So the time, if we look from C's perspective, the time from when the frame started to be transmitted from A until it has arrived at C, during this period, C is unaware of A's transmission. And then C, if C senses the channel during this time, it will think it's idle and then would transmit its frame, right? So this is sometimes called the vulnerable period. It's the time when sensing does not prevent a collision, right? And the time this is equal to t prop, the propagation time from A to Z. Okay, and then what we call propagation time here is the longest. Okay, so A and C are the physically most distant nodes in this network. Okay, right. But then suppose then we have maximum unluckiness here in the sense that that C, just a fraction of time before the frame from A arrives, sends the channel and then starts to transmit its frame here. Then this is allowed, right, through the protocol. But then at this point in time, C, by listening to the channel, knows, oh, there is a collision on the medium, and then ceases to transmit its frame. At this and it ceases to transmit the frame here. So C stops. Okay. A on the other side has no idea but that C has started to transmit. So A will happily continue to transmit its frame until this point in time. This is the time when A knows that C has transmitted something. Right? And then A can then stop its transmission. And now to detect C's frame here, C needs to transmit for a little bit of time here, because otherwise this will not be detected by A, right? So that's why you don't immediately stop transmitting when you detect a collision. You continue for a short period of time here. Okay, and then A does the same, continue for a short period of time before it stops its transmission. Okay, so then after this time, the signaling stops, right? So A stops here. Okay, right. So what can we say about this then? Well, from A's perspective, the longest time it will take for A to detect any other ongoing transmissions is twice the propagation time. Right? It takes T-prop to go over to the other side. It takes T-prop from the other frame to get back to A. So it's like the round trip time here. 2 T-prop. Right? If A, after 2 T-prop, has not detected a collision, it knows that there will be no collision, because then sensing will prevent all other nodes from transmitting. Right? But for a period of time, T-prop time, the furthest away node can start to initiate its transmission. And since you take T-prop to get back, during 2 T-prop seconds, A is unsure about whether there will be a collision or not. But after 2 T-prop, it knows either it's been a collision and it's able to detect it, or there will be no collision. Was that clear? Right. So then we can think of this as some type of coordination time. This is the time it takes to coordinate access to the channel. And in this case, when there was a collision, then you have to back off a little bit, and then you have to retry. Okay, and hopefully better luck next time. Right? No guarantee, but hopefully, right? Okay. So to summarize this, for this analysis to hold, the assumption is that the minimum frame length is 2t prop. Okay, because if the green frame here ends before 2t prop, it will never be able to detect that there was a collision, because then there is another frame coming a little bit later, and the A will not transmit at the same time as it receives a frame from the other side. And it will not then be able to detect a collision at node B. So we need a minimum frame duration of at least 2t prop for this to work, collision detection. So this is a crucial thing, that there is a minimum frame duration, and we will see how that is implemented in Ethernet in a while. Okay, now if there is no collision detected during this contention period, so this is called the contention period, then the node knows that it has successfully captured the channel, so that there will be no other activity on the channel as long as it transmits its frame. Okay, questions? Okay. Now, if we didn't have collision detection, what would happen then? Well, then A would continue to transmit its frame for potentially a very, very long time, right? And the same thing for C, for a very long time. Both of them have to wait for their timers to time out when they don't get an acknowledgement, and then retry. Okay. So collision detection has two advantages. First of all, we don't spend a lot of time transmitting frames that would never get through, so we can quickly recover from this, right? Well, basically that's it, right? You can abort the transmission you know that will not be successful anyways, and then the channel becomes idle, and then it can become useful for somebody else or for yourself, right? And you don't have to wait for the ARQ protocol to do its thing. Okay, so here is a flow diagram. If you rather like flow diagrams, this I encourage you to go through this. In this, we also have details on how to calculate the back-off time. And essentially it's like this. At the first time when we transmit, okay, we have a data to be transmitted at this, goes down here, and we put the counter k to equal to 0. K is the number of retransmissions. And then we have one of the persistent methods here. So for instance, one persistent, p persistent, or non-persistent. Okay, very, very ugly handwriting, but hopefully you heard me. Then we start to transmit, and then during the transmission, we look for if there is a collision or not. As long as there is no collision, we keep on transmitting. However, if there is a collision, then we go down here, and then, if there is collision during the transmission, we abort the transmission and send this short jamming signal that basically we continue to transmit for a short while, and that is to inform the rest of the nodes that the collision has occurred. We increment k to k plus 1, and if k is equal to k max, then we abort everything. So there is a maximum number of retransmission attempts here. If k is less than k max, then we generate a random number, and r here is chosen to be 0, 1, 2, up to 2 to the power of k minus 1. So that means that for every turn we go around here, we increase the possible numbers that r can take on, and that means that we essentially increase the maximum back-off time, and therefore the back-off time tends to become longer. Okay, and then we wait for the back-off time to expire, and then we continue again. Okay, so we keep on going around here. Okay, and the reason why we want to wait for an extended period of time here is that whenever we are in back-off, The reason for the back off is that we would like to resolve collisions. If two nodes go in and collide, they wait for random back off times, and with some luck, they are such that their retransmission events occur, so there is no more collision, right? So if we have two nodes, say 1 and 2, and there is a collision, then 1 waits for the back off time for node number 1. So that's a random variable. And then node 2 waits for a back off time, which is a random variable for node number 2. If these are separated wide enough, then there will be no collision between 1 and 2 the next time, right? Now, we want to wait as short as possible, but as long as possible so we can make sure that there is no collision. So as little as possible, but long enough, right? How long do we need to wait? Well, it depends on how many nodes who are competing for the channel at the same time. So for instance, if we had the third node here, there will be a back off time for that one too, B3, TB3, or the fourth node, or the fifth node, and sixth node, and so forth. So the more nodes who are waiting to access the channel at the same time, the longer the maximum back off time needs to be in order to well separate these. Okay, so maybe this is the maximum back off time chosen by the protocol, and then this one moves to the right when k increases. Okay, so for every time a node detects a collision, it increases the maximum back off time. So then we increase the probability of success for the next retransmission. If there is still a collision, it means that, okay, maybe the maximum back off time was not long enough. So we increase that, and we increase that, and increase, and so forth. And the reason why we do this is because when we have a collision, we don't know if we collide with one other node, or two other nodes, or three other nodes, or four other nodes. And the maximum back off time here should be selected according to how many nodes at this particular point in time is trying to access the channel. Okay, so this algorithm does a pretty good job at it. It starts with a small TB max and then increase that. It doubles it for every time there is another retransmission event. This is called a binary exponential back-off window. Okay, any questions? Okay, so then what is the performance of this? We will not go through the analysis of this because it's a little bit, I don't know, it's a little bit tricky to do this, and one can question whether this is correct or not. But this equation is often claimed in the literature as showing what the maximum load we can support with the collision CSMA with collision detection. And we see that rho max, the maximum load we can have. And remember that this is always a number which is less or equal to 1. Okay, and it's given as follows: 1 over 1 plus 2e plus 1 times a. Okay, so a again is this normalized delay bandwidth product. So basically a becomes large when t prop is significant compared to tf, when we can fit in many frames on the medium at the same time. And then e here is the regular e, right? E to the something, 2.7. Okay, and this, if you wonder where this E comes from, is basically from slotted ALOA. So that's part of the analysis here, right? But the analysis is sort of like a little bit funky, so it's not completely correct, and you can always question the assumptions. But anyways, this is often quoted. in the literature. And this is better than with the CSMA without collision detection. It should be, right? And it's also better than ALOA for small a. So here I will show you a picture here where I have no idea how this picture was created. I just picked it out of a book and it was not very explicit on what happened here. But it illustrates a point which makes sense. That's why I put it up here. So if we look at rho max, that's the maximum load we can support as we increase A. What is it? Okay. And if we take ALOA, for instance, the basic pure ALOA, we know that the maximum throughput we can have is about 18%, 0.2, right? And as a matter of fact, it doesn't matter what value of A is. It will be the same regardless. For slotted ALOA, it's twice this, so it's like this. Now, this curve here is only true if we ignore guard times, which is needed for slotted ALOA to work. So I would expect slotted ALOA maximum throughput go down. I don't know where, but eventually it will go beyond ALOA. Right? ALOA will be fixed. That is clear. Okay, and then we have these curves. Then collision. Let's go with the CSMA. So one persistent CSMA here will go like this. It's claimed. And then non-persistent CSMA will go something like this, and CSMA with collision detection would be the best. Now, these are without collision detection, and this one is with collision detection. So if you have collision detection, you should do better than without collision detection. But the interesting thing about this is that whatever you do, at some point A is large enough so you might as well go with ALOA. Right? That's just a fact of life, right? And the reason for this is that it's very, very hard to do coordination when there is a long delays compared to the frame duration. It's just the way it is. Okay, so let's take 15 minutes before we go in. Okay, so one final thing before the break. There is also something called CSMA with collision avoidance, which is used in Wi-Fi, for instance. We'll postpone the discussion of that until we get into the Wi-Fi lecture in maybe next week, I think, if I remember correctly. And after the break, we will go into controlled access methods. Okay, so let's take 15 minutes from now. Yep.
In the slides about the flow diagram, I just want a little bit of clarification because I think something was wrong.
Oh, let's look at it. Which one?
For that one, I think. No, wait, you were there. That one, sorry. So here, if k equals to k max, shouldn't the true
okay,
false be
thank you.
shifted? Yeah,
Thank you.
No worries.